Hi, folks. I'm glad at least a couple of you found your way back, and we'll wait for a few minutes for the others. My live stream died, so that happens. Hi, it's Bella. So as soon as I get a few more back, we'll continue with our pendulum. That is the name of it. And in the meantime, let's play with it a little bit. So there it is. And notice what happens. Hi, everybody. Thanks for coming back. We're just playing around, waiting for others to join us. Watch what happens when I make the length less, or even less. Oh, it changes the pendulum, doesn't it? It really changes it. Sig figs, just round to at least 2 sig figs, okay? All right, so I got enough of you back. Let's go ahead and continue with the pendulum. Okay, and what we really got to get, dang it, before I get out of here with you, is we need to understand for a harmonic oscillator, including the pendulum, where's the equilibrium position? Where will it be? Where do you suppose we say it's at equilibrium? Hi, thanks for coming back. And where would the pendulum be? Where do you think? In what position would it be in equilibrium? Because I got to draw it before we run out of time here. What position would the pendulum be in where it's at equilibrium? In the middle. Thanks, Noah. So here it is. So that is the equilibrium position. Now, let's talk about what a harmonic oscillator is, okay? Let me erase this other version of it. Harmony, when things are in harmony, thanks, a lot of you notice that it's in the middle, good. So a harmonic oscillator is movement back and forth from an equilibrium position so movement back and forth from an equilibrium position that is, so the movement is symmetric in here and here. Okay, so what am I talking about? Let's get the mouse going. As I go back and forth with the mouse, What's the same on both sides? There's the equilibrium position. What's symmetric on both sides of the equilibrium position? Two different things. Let's see if you can guess one of them at least. Okay. What's symmetric on both sides of the middle or equilibrium position? Velocity's kind of symmetric, but to be honest, no, it's varying all the time. Like it's fastest in the middle, but it's stopped at the ends. So height is symmetric. Good, Magdalena. Let's go back to something else. Distance. Yeah, a couple of you said distance, and that's one thing for sure. It's going to go the same distance here as here. Okay, what else? Height is not what I'm looking for. That's kind of another type of distance. What's the same on both sides of the equilibrium position that I could measure? And it's not velocity, because the velocity is changing all the time. It's fast in the middle, slow at the ends. It's symmetric, but that's not one easily measured. So something easy to measure on both sides of the equilibrium position other than distance. Something you and I have measured in this class. Hurry up before something runs out. Hint, hint. Amperage. Oh, come on, people. Amplitude. Oh, my God, please. What else could you measure? Come on, it's a basic thing of, Lily, time, okay? So turns out it's going to be going the same amount of time here to here as here to here, okay? So that's got to be symmetric as well. So it's got to be symmetric in distance and time on either side of this. So moving out to here or moving out to here, it better be the same distance and amount of time for each spot. Okay? Ute. Let's do a couple other examples of harmonic oscillators in our time remaining. Okay, I'm going to erase this picture, but not my definition yet, because you might still be writing, because I lost you, because I crashed. That happens. Another examples. What's something in your earthquake lab which is acting as a harmonic oscillator? Something in your earthquake lab that is acting as a harmonic oscillator. And yes, Shilpa, you're right. That would also be, but it's not part of the definition. And it's related to height, which is related to distance. Okay, what's from your earthquake lab that would also be essentially a harmonic oscillator? If you've ever been in one on a windy day, you know what that is. Right, thanks, Magdalena. Buildings, tall buildings. Whoa. So if you're in a skyscraper, turns out they go back and forth at the top. Did you know that? They're supposed to. If they didn't, they would be brittle and they'd break. So there's a little give and take in every skyscraper, right? Especially if you're in a place like Chicago with a lot of wind, they've got to be able to take that and a certain flexibility, believe it or not, in the steel and concrete that makes up the building. They got to be able to go back and forth. So essentially, they're a harmonic oscillator, aren't they? And the equilibrium position is where? Well, of course, when it's not moving, it's just like that. That's the equilibrium position. Then it's symmetric in time and distance, just like a pendulum is. What's another thing we studied? Another something that's built that's a harmonic oscillator. Last thing before we run out of time. Harmonic oscillator. We saw a video of this. I'll start drawing it because I'm running out of time. Oh, suspension bridges. Remember how they go up and down? Not all bridges, but suspension bridges are harmonic oscillators. They're supposed to go up and down, just not as much as the Tacoma Narrows did, right? Because then it broke it. Suspension bridges. Good. We'll look at another kind of harmonic oscillator and talk about measurements and stuff a little more next time. Okay, so our time is over. Thanks for joining me. I'll send this little tiny video out to those that missed the rest so you can tell them they can watch it. Unfortunately, the first part is lost forever. I had to delete it, but you guys were here. Unfortunately, a couple that were not here. That's the way it goes. Okay, bye-bye. I'll send this to you on the Google stream, okay? And everybody will have this little video at least, those that couldn't make it back.